to mutual inductance. We have started this topic earlier. Today also we have seen it briefly, and then we'll switch to the numerical or question based on the mutual inductance. What we have seen in the last class is if you are taking two coils L1 and L2, they are very near to each other. Okay, L1 and L2, where L1 is the self-inductance of the coil 1, L2 is the self-inductance of the coil 2. If we are flowing the current in this I1, let's say, so we know the magnetic field will generate around it. Okay, and this is the phenomena that inductor stored the energy in the form of magnetic field. We know about this. If similarly in the L2, if current I2 is flowing, it will be having its own magnetic field. Okay, the L2 will also generate the magnetic field. It means I can say the magnetic field of coil L1 will affect the parameters of L2. Is it okay? Because the magnetic field will be linked to L2. Magnetic field of L1 will link to L2. So magnetic field will generate something. Because of I1, I am getting magnetic field. And in the inductor, if we'll change the magnetic field, we'll get the current. Okay, like this. Sorry. So, I can say they are mutually doing something. Means they are sharing their magnetic field mutually. So, sharing of this magnetic field is nothing but the mutual inductance. Due to magnetic field, we are having inductance L1. Due to magnetic field, we are having inductance L2. Due to this sharing magnetic field, we are having mutual inductance. Is it okay? Denoted by M. Denoted by M. How it will affect? It is given over here. See, this is the primary coil. The voltage is V1. This is the secondary coil. Voltage is V2. In this, assume current I1. In this, assume current I2. I1 is flowing in this circuit. Will drop some voltage over here. Because you know the voltage in the inductor L di by dt. L di by dt. Yes, it will drop something. But at the same time, it will get some voltage drop because of this I2. Remember, the I2 is affecting primary. I1 is affecting secondary because of the mutual inductance. So, we have to write the parameter related to I2 also. So, it will be given by, see over here, the V1. Suppose I am getting V1 over here because of second I2. So, I'll write it M12. Means 1 to 2, we are looking for mutual inductance into di2 by dt. The voltage developed in the primary due to the current in the secondary. This is nothing but the mutual inductance concept. If they are mutually, if they are neighbor to each other, they will affect to each other. So I can say the mutual inductance is the ability of one inductor to induce a voltage across a neighboring inductor measured in Henry. The unit of the L and M is Henry. Both are same thing. L is self, M is mutual. Okay. Now come to the series and series opposing and series aiding concepts. What is series aiding concept? Suppose these are denoted by dot. What this dot is denoting? Dot says if the current in this primary is coming to this direction, current in the secondary is coming to this direction, means the same direction. So I can say they are in series aiding. But instead of this, the current is coming from this direction. Dot is showing that the current is entering in the circuit. Here it's showing the current is out into the circuit. When you are getting dot, when you are exiting the circuit, okay, this current will exit from this point. So at the outing, when current is going to out from the coil, it's getting dot. In this case, current is getting dot. When it's entering to the coil, it is series opposition conducting. But if the current is coming to this direction, in this the current is coming to this direction, they are in series aiding. See, I'll show you here. If this is L1, this is L2. Dot is given over here like this. The mutual inductance is given in between them is M1. 2 points AB. Between A and B you have to find L equivalent. Right? What L equivalent means? If the mutual inductance is not given, simply you will write L equivalent is L1 plus L2 because the inductors connected in the series are simply added like resistance. Okay, but here new concept is given, mutual inductance. Mutual inductance is given, okay fine, but with dot notation. This dot indicates this. For L1 and L2, both the current is entering to this terminal. Means when the current is entering, it's getting dot at the entering point. See, if the I1 is flowing in the circuit, for the L1, where the I1 is facing the dot at the entering stage. For L2, where the I1 is facing the dot at the entering stage. Entering stage, they are series adding. In the series adding, the equivalent will be given by L1 plus L2 plus 2M. Simply you have to add 2M. But suppose if they are in series opposition. Series opposition means instead of this dot, we are having another dot and over here. But it indicates for the same circuit current is flowing I1. For the L1 current is getting dot at entering stage, but for the L2 current is getting dot at the outing stage. So they are connected in series opposition. While when the two inductors are connected in the series opposition, the equivalent is given by L1 plus L2 minus 2M. I hope this is clear to you. So this is the concept, and I'll illustrate the concept in the next problem. We'll see over here. See. The question is given, calculate the phasor currents I1 and I2 in the circuit. The circuit is given over here. If you'll assume or if you'll take the circuit in your hand, you'll get the I1 current is given like this and I2 current is given like this. This is I2. First, please identify the circuit is series opposition or series adding. This is series opposition or series adding. In this, they are given current already. So we have to go with this currents notations. If they are not given the currents, we have to assume our currents, but they have given. So we will go to their notation. So in this, for this inductor, current is entering from this side and getting dot at the entering stage. Okay, fine. For the second inductor or second coil, the current is getting dot at the outing stage. The current is entering from this direction. So this is series opposition. Series opposition. Okay. This is series opposition connection. Now we'll move to the circuit solution. All parameters are given in the form of reactances. See, this is not inductance, this is the reactance. So simply I can apply node analysis or mesh analysis, whatever I want. I'll apply mesh analysis in this. Okay, because I1 circuit currents are given, so it will be better to go with mesh analysis. First, I'll write the mesh analysis for A, B, C, and D. I will write for A, B, C, D. Mesh analysis. I'm getting battery 12 with positive sign. Come to minus 4J. This is minus sign outside. We are getting minus 4J. Multiply with I1. Take it capital I1. Okay, fine. Here you are getting minus 5J. Minus is the drop and the current is I1. At the same stage you are getting another voltage also because of the I2. Mutual inductance is given. So minus is for drop. They are connected in series opposition or series adding. They are connected in series opposition. So minus sign. Minus sign and voltage drop is 3J. This is 3J multiply with I2. Simply equal to 0. Is it clear to you? This minus sign because of the voltage drop we are considering, and this minus sign because of the series opposition. Now if you will resolve this equation, you will get 4ji1 minus 5ji1 plus 3ji2 equal to 0. Okay, so your equation is, this is ji1 plus 3ji2 equal to 0. So this 12 you will take to this side and you will get finally ji1 minus 3ji2 equal to 12. Equation 1. Is it okay to you? Come to the second one. If you will be having any doubt, it will be cleared over here. EFGH. Take the mesh EFGH. Okay, we'll start from here. I'm getting 12i2 with negative sign because drop is like this. 12i2 is fine. I'm getting this minus, because of the drop, 6ji2. Minus for the drop, they are connected in a series of positions. Again minus sign. 3j into current of primary equal to 0. Any doubt you have in this term? Any doubt? This negative sign I'm writing for the series of position connection and this minus sign because of the drop like this. So at the final stage we are getting 12i2 minus 6ji2 minus plus. I'm extremely sorry for this. Minus plus. This is 3ji1 equal to 0. Finally, this is 3ji1 minus 12 plus 6ji2 equal to 0. Equation 2. Okay. So finally, you are remained with 2 equations and 2 unknown. You can solve this I1 and I2. I'm telling you what you are getting to get. You are getting, after solving you will get I1 is nothing but 13.01 at an angle minus 49.53. You will get I2 2.91 at an angle 14 and something ampere. These are the currents given, I1 and I2. So I hope the concept is clear. Mutual inductance concept is clear. Now we will move to the next. This is the transformer circuit. See, the transformer circuit, this formula is very useful for some problems coming into the gate. That's why I'm considering over here. Please observe this. This is the circuit for transformer. In the transformer, we have primary and secondary. Primary having some turns, suppose N1, secondary has some turns N2, right? The direction of the current is like this. We'll connect ZL load. In the load, we are getting current from the transformer. And see, because of this I1, some voltage will develop into this. And due to voltage magnetic field, though this is the coil, it will generate magnetic field. That magnetic field will link to the secondary coil and will generate some voltage in the secondary. And due to that, we are facing this, or we are getting this current I2. Right? So this is the transformer circuit. So here we can get the current in secondary because of the primary. Okay. So transformer is also 2 types, step down and step up. Step down will suppose here high current is there. In the secondary it can down the current. Okay. And this is the very low current. In the secondary it can up the current. Right. So what is the relation actually? My fundamental focus will be on the relation between voltage and current in the transformer circuit. In the transformer circuit, the relation is like V1 by V2 equal to I2 by I1. And it will be equal to N1 by N2. This is the relation for transformers. V1, I1, what it means? The power transferred, energy conservation law, you can say. What is the power over here? V1, I1 will be over on the second stage also, V2, I2. This will be constant, right? The power delivered should be equal to power absorbed. So this is Vi, V1 I1 equal to V2 I2. So by this equation, V1 by V2 is nothing but I2 by I1. This is one relation. But in relation in terms of these terms, it will be like this. So if you want to write the current equation, you will write I2 by I1 equal to N1 by N2. But if you write the voltage equations, it will be V1 by V2 equal to N1 by N2. Is it clear to you? Now another formula, and this is also very important formula, the ZL in terms of input. ZL in terms of input. See, ZL, this ZL given as, you will see here Zn. This is N2, right? N2 is 1. So I can write ZL is nothing but N2 by N1 whole square into Zn. Want to find out the value of ZL in terms of Zn. So yes, ZL equal to Zn. No problem at all. But here the turns ratio will be there. N2 N1 square. We will consider N2 by N1 whole square into Zn. I'm sorry. So this is about the transformer circuit. This is very important formula. 2 or 3 times you got the questions from this formula only in the gate under electrical and instrumentation. Please remember this equation also. V1 by V2, I2 by I1, N1 by N2. I hope this is clear to you. Now the next topic is two-port networks. Two-port networks. What is the two-port networks? If you consider any linear network over here and you are taking input and output from two sides. So I'll take it two-port networks because you are having two ports. One is, see, this is the input stage or stage 1. This is stage 2. In the two-port networks, the current is entering into the circuit. The current is entering to the circuit. And from the circuit, you will take the output. Right? So the two-port network is an electrical network with two separate ports for input and output. Okay? You can take output over here. You can take output over here. Okay? This is the transmission line kind of thing you can compare with. Okay? I'll tell you. So the two-port network consists of so many types we are having, but we'll consider only 4 types. Z parameters, Y parameters, H parameters, and T parameters. Okay? We'll see this 4 only. What is the Z parameter? See, this is the, we have seen the, this is the, given for the two-port network, right? V1, I1, V2, I2. So there will be some relation between this V1, I1, I2 and V2 because we are having only 4 parameters. 2 parameters belong to the input stage, 2 parameters belong to the output stage if you consider this as output stage. So the relation between these 4 parameters constitute 4 different types of connection or two-port networks. We are having so many types, but we'll consider this 4 only. The first one is the Z parameter. Z is nothing but the simple impedance. The terms Z are called the impedance parameters or simply Z parameters and have units of ohm. Means totally it's like a resistance kind of thing. Equation will be V equal to Ri. Whatever equation we'll write will be resembled to V equal to Ri because we are writing the impedance parameter. Is it clear? So for this equation or for this port, Z parameters are given V1 equal to Z11 I1 plus Z12 I2. See, the V1 is given in terms of I1 and I2. So for I1, it's taking Z11, I2 is taking Z12. This is similar V equal to Ri. Means we are writing the voltage equation in this form. Here is the voltage, here is the form. right? Because we are facing two currents in the two-port network, so we can denote V1 in terms of two currents. What about V2? V2 is also Z21I1 plus Z12I2. This is the equation given for the Z parameters. Okay. Now, can we calculate separate V1, V2, V3, V1, V2, I1, I2? Yes, we can calculate. How? If you want to calculate a V1 by I1, means you want to calculate Z11 input stage impedance, only input stage impedance. So you have to make sure that your I2 will be 0. You have to make sure that your I2 should be 0. If I2 is 0 in this circuit, so from this equation you will get V1 by I1, and that will be equal to Z11. That will be equal to Z11. So Z11 is nothing but V1 by I1 when I2 is equal to 0. Is it okay to you people? What about Z12? You will get Z12 when you are open I1, when I1 equal to 0. So this is open circuit, means you are doing open circuits, right? What I mean is, suppose you want to get I2 equal to 0. What you will do? You will open the circuit simply. If you will open the circuit, I can say this parameter is the open circuit parameter also. Open circuit parameters. Is it clear to you? Now, come to the next one. Okay, let's see this. Since the Z parameters are obtained by open circuiting the input or output port, they are also called the open circuit impedance parameter. What is Z11? Open circuit input impedance. Why input impedance? Because at input stage, whatever this circuit is, in the circuit the current is going I1. I1 is going from the V1. If someone will ask, what is the resistance? This one. You will say V1 by I1. This V1 by I1 is given by Z11 by Z parameter. So this is the open circuit input impedance. Why open circuit? Because at the last, this stage, we open the circuit. Z12. Now come to the Z12. Open circuit transfer impedance. See, what is the Z12 actually? Z12, V1 by I2. You are considering V1 from this stage, but you are taking I2 from that stage. Means the impedance because of I2 and V1 is Z12, right? So I can write the Z12 is open circuit. All are open circuit. Forget about this. Transfer impedance from port 1 to 2. This is the transfer kind of thing now. That's why it's called the transfer impedance. Similarly, Z21 will be the transfer impedance. Right? What is the Z22? It will be output impedance because you are getting Z22 equal to V2 by I2. Output stage voltage, output stage current. So Z22 is the output stage impedance. Now come to the, sometimes Z11 and Z22 are called the driving point impedance. These are the driving point impedances. Z1 and Z22. Because of these are the equivalent resistance or impedance of the circuit between two ports, while second is opened. While Z12 and Z2 are called the transfer impedance. Z12 and Z21, they are the transfer impedances. Z11 and Z22, they are called the driving point impedance. Now we are having some conditions. If by calculating this problem or solving this problem, suppose we are getting Z11 equal to Z22. Suppose we are getting Z11 equal to Z22, means a symmetry. Symmetry means from any direction the circuit is same for you. Okay, so this is about the symmetry. The circuit will be symmetry. From the both direction it's looking same. What about the reciprocal? Reciprocal, if Z12 equal to Z21. If Z12 equal to Z21, then circuit will be reciprocal. Is it okay? Come to the next. The problem is given over here. Find the I1 and I2 in the circuit. I1 and I2 in the circuit given over here. The parameters are given. If parameters are given, can you apply the equations? Equation is Z11 I1 plus Z12 I2 V2 is nothing but Z21I1 plus Z22I2, right? Equation 1 and equation 2. I can write the equation 1. V1 equal to Z11 is given 40I1 plus Z12 is given 20I2. V1 is given directly 100. So instead of V1, I can write 100. This is equation 1. Come to the equation 2. Equation 2, V2. V2, Z21. What is Z21 given over here? 30J I1 plus Z22. Z2 is 50 I2. Can you solve these two equations? No, because you are having three variables. You have to remove this V2. What is this V2? V2 is the voltage drop across here, 10 ohm resistor. The current is coming from this circuit like this. Because of this, the drop will be like this. Is it okay? Because of this current, drop over here will be 10 I2. And V2 and this drop is opposite to each other. So V2 is nothing but minus 10 I2. So we will replace this V2 by minus 10 I2. This is 30 JI1 plus 50 I2. I'll take this to this side. So this is 30 JI1 plus 60 I2 equal to 0. Now you are having two equations and two unknowns, I1 and I2. Can you solve for I1 and I2? Yes. Where is the first equation? This is the first equation. 40I1 plus 20JI2 equal to 100. And this is 30JI1 plus 60I2. So you can solve this. Finally you will get I1 and I2 equal to, we'll get I1 equal to 2 at an angle 0 and I2 equal to 1 minus 90. Okay, so this is Z parameter. I hope this is clear to you. Come to the next one. The next one is admittance parameter. And you know admittance is reciprocal of impedance. Correct? Admittance is denoted by Y. Impedance is denoted by Z. Reciprocal of impedance is nothing but admittance. So, what is the Ohm equation? V equal to Ri. Right? So, V by R equal to I. So, I 1 by I can write Y, impedance, into V. So, in this the equation will be like this. I1 will be here, Y1 something will be there, and V2 is like this. Equation will be I, Y, V. I equal to Y, V equation. So, this is the diagram given over here. I1 input stage, V1 output stage, I2 and V2. This is the linear circuit or linear network. The equation is given over here, or Y parameter is given by this two equations. I1 first stage current is nothing but Y11 V1 plus Y12 V2. I2 equal to Y21 V1 plus Y22 V2. Is it okay to you? Good. So the equation C, we have seen the equation will be in the format of YV. Here is the Y terms, this is the V terms. V terms, Y term. And here is the I terms. Now, if you want to calculate Y11, suppose your task is to calculate Y11. What you will do, you'll turn off this first. So V2 equal to, V2 should be 0. Once V2, you see, once you turn off the V2, means V2 equal to 0, we are getting Y11, and the Y1 is nothing, 1 is nothing but I1 by V1. I1 by V1. Similarly, you can calculate all four terms, Y11, Y12, Y21 and Y22. So friends, if you observe over here, for calculating all these four terms, in the secondary or in the second stage or output stage, you are doing turn of the voltage. How to turn off the voltage? Suppose you want to turn off the voltage, you will short it. Is it okay? Between these 2 points, if you want to turn off this V2, you will short them. Because of this short circuiting, the V2 becomes 0. There is no voltage difference. So I can say this parameter as a short circuit parameters also. Since the Y parameters are obtained by short circuiting the input or output port, they are also called the short circuit admittance parameter. Specifically, see, Y11 is nothing but short circuit. All are short circuited. I will not talk about these 4 terms. Y1 is nothing but input admittance. Is it clear to you? Y11 is the input admittance, Y12 is the output admittance. And what about Y12 and Y21? They will be transfer admittance. They will be transfer admittance. Though we want to get Y12 means the admittance is transferred from 2 to port 1. Is it okay? Now here also we are having 2 conditions for the symmetry and for the reciprocal. If Y11 equal to Y22 we are getting, then circuit will be symmetric. In the both direction we are getting the same values. For the reciprocal, Y12 will be equal to Y21. Very simple. Y12 equal to Y21. For the Z parameter, symmetry is Z11, Z22. For the Y parameter, symmetry is Y1 equal to Y22. This is nothing but symmetry. What about reciprocity? Reciprocity Z21 will be equal to Z12, Y21 equal to Y12. This is the reciprocity. Is it clear to you? Come to the H parameters now. This is the hybrid parameter. Hybrid means for the last 2 networks, linear networks, we are taking, see, if this is V1 into the circuit, because of this I1, here is I2, this is V2. We are simply taking V1 in terms of I1 and I2, V2 in terms of I1 and I2, or in the second stage we took I1 in terms of V1 and V2, I2 in terms of V1 and V2. But here in the hybrid parameter, we will take V1 in terms of current and voltage. First, I'll take the V1 in terms of input current and output voltage. The equation is like V1 equal to H11I1 plus H12 V2. This is the hybrid parameters. So input voltage is given in terms of input current and output voltage. Similarly, the output current will be given H21I1 plus H22 V2. The output current is given in terms of input current and output voltage itself. Okay, so this is hybrid parameter equations. Now the H terms are known as the hybrid parameter or simply H parameter because they are a hybrid combination of the ratios. This thing we have done earlier. If you want to calculate H11, you have to turn off this. You have to turn off V2. You will get H11. If you want to calculate H12, you have to turn off I1. Like this. It means in this H parameter, you are shorting also. You are performing short circuits and you are performing open circuits also to get the different values of H11, H12, H21 and H22. Is it okay? Now this one is the very important transmission parameter or also called the ABCD parameter. This one is very important. Okay. So many times we have, getting the questions in GATE examination from this concept. So come to the transmission parameters. In the transmission, this is the symbol of transmission lines from the power source. We are generating the current and we are transferring it to one place to another place like this. This is similar to the, see, this is one electric pole. In this electric pole we are getting 2 wires, suppose 2 terminals, and at the output stage we are getting 2 terminals. Here the current is coming, here the current is going. That's why I'm considering outgoing current, incoming current, outgoing currents. Okay. So come to the basic. They are useful in the analysis of transmission lines such as cable and fiber because they express sending end variables V1 and I1. Where is the V1? V1. Where is the I1? I1. In terms of the receiving ends, variable V2 and I2. The receiving end we are getting V2 and I2. At this stage, input stage, we are giving V1 I1. The output stage we are getting V2 I2. Simple. For this reason, they are called the transmission parameters. They are also called as ABCD parameters. They are used in to design the telephone systems, microwave networks and radars. Okay. Come to the equations. Now, the equations are V1, this V1 will be given in terms of output parameters, B8. This I2 will be minus because for the two port network, earlier we have seen I1 and I2 in this direction, but for this we are changing the direction and making it outgoing. So that's why I am taking it minus sign over here. So V1 is AV2 minus BI2 and I1. We are relating the input terms in terms of output parameters. I1 will be CV2 minus DI2. Two equations. You can calculate A, B, C, D also for this. A, V1 by V2, I2 equal to 0. B, like this you can calculate it. This is ABCD parameters. Now come to the problem actually. See, 1 and 2 problems we are having. First I'll take this T based problem. This circuit is given over here is this, and we have to calculate I1 and I2. I'll draw this circuit on the fresh page, then we'll start to solve it. So given circuit is, let me draw it again here, 2, 14 at an angle 0. The network is given T and here 10 ohm. The voltage is V2. The current is I2. In this the current is I1 and the T circuit is given. This T is given 5, 10, 0.4 and 1. Okay. Means for this circuit, if the voltage over here is V1, take its V1, the current in this is I1, and for this circuit, the voltage over here is V2, and the current is in this way. Then I can write this equation V1 equal to A I2, A is 5, V2 minus 10 I2. Is it okay? If the current is outgoing, but here the current is incoming. So for this particular one, I can write plus because the current is opposite. Now come to the I1. I1 is 0.4 V2, again plus sign, and I2. This is the circuit for this particular one. Okay. Two equations you are having, 1 and 2. V1 equal to 5 V2 plus 10 I2, I1, and the question is calculate I1 and I2. Now I'll replace. What is the V2? What is V2? V2 is, this V2 is minus 10 I2. I2 is coming to this direction, it will make some drop over here and drop value will be 10I2. 10I2 and V2 is the drop given ready-madely. So V2 is minus 10I2, equation 1. Is it okay? You can replace it over here. So it will be I1 0.4 minus 10I2 plus I2. So this will be minus 4I2 plus I2 equal to I1. Is it clear? So finally you are getting I1 equal to minus 3I2. One relation you got. Now at the input stage also I'll remove this V1. The current is given over here I1. And I1 is nothing but 14 at an angle 0. I can remove 0, no problem at all. V1 potential difference divided by 2. So for this equation, by this equation I can remove V1 in the equation 1. So 2I1 equal to 14 minus V1. So V1 equal to 14 minus 2I1. Okay, I'll replace this V1 over here. Instead of this, you have now 14 minus 2I1, 14 minus 2I1. Okay. So I'm going to solve this equation. The equation is 14 minus 2I1 equal to 5V2. V2 is given over here. So can I write it? Minus 50 I2. Yes, I can. Plus 10I2. 14 minus 2I1 minus 40I2. Right? So 2I1 minus 40I2 equal to 14. Another equation is this, I1 equal to minus 3I2. So 2 minus 3I2 minus 40I2 equal to 14. So minus 6I2 minus 40I2 equal to 14. So I2 is equal to minus 14 divided by 46. 7 divided by 23. Negative. This is I2. Now you can calculate I1 also. I1 is minus 3 minus 7 by 23. Minus minus become plus 21 by 23 ampere. So this is the solution of that circuit. I think I have done some mistakes over here. Please check it, because at the output you should get I1 is equal to 1 ampere and I2 equal to minus 0.2 ampere. Okay, it's calculation mistake. You can check it or you can do it again, so you'll get the answer. And please match your answer with this. I1 equal to 1 ampere and I2 equal to minus 0.2 ampere. Okay, this is the question I'm leaving for you. They're asking find the transmission parameters, means again they're asking for ABCD parameters. You can find it. I'm leaving this circuit for you. Come to the next. Interconnections. Now Z parameters can be added if networks are connected in series. These are the two networks, NA and NB. They are connected. This is the series combination. This is the series combination. Okay. If they are connected in such a way, so the resultant Z matrix will be the summation of individual parameters. Whatever parameters Z11 for A, you will add with Z11B, Z12A, Z1B. So we are adding. So whenever the Z parameters are connected in series, the Z parameters. Please focus on the Z only. The Z parameters are connected in series. So the resultant is given by just adding the separate parameters. Y parameters. If Y parameters are connected in parallel connection, so we can add the Y parameters. We can add the Y parameters, but Y parameters or two networks should be connected in parallel combination. So this is nothing but the parallel combination. The I1 is going into both of them. This is connected with the both of them. This is the output stage, like this. They are connected in parallel combination. And in the parallel combination, the Y parameters can be added. It's given by Y11A, Y11B, V1, like this. As simple as that. Very important. Two networks are said to be cascaded when the output of one is the input of the other. See, the output of this is behaving the input of NB, like this, and if the networks are connected in such a way, I can say the T parameters can be, we can multiply the matrix form. The parameters of this is given over here. The parameters is given over here. The whole parameters of the circuit is given by this. And this is nothing but the individual parameters. And this is the multiplication of the matrix. Is it okay? Now come to the resonance. It's very important topic as per the GATE exam. Very important. And nowadays we are getting so many questions every year in electrical instrumentation and electronics from resonance concept only. So what is resonance? I think you know about this already. So the concept of the resonance applies in several areas of science and engineering. Resonance occurs in any system that has a complex conjugate pair. This is the must condition for resonance, that it should contain capacitor and inductor in it, because they are providing the complex conjugate pairs. It is the cause of oscillations of stored energy from one form to another. It is the phenomenon that allows frequency discrimination in communications network. Now this one is the important point. Resonance occurs in any circuit that has at least one inductor and one capacitor. At least one. This is must condition, that in the circuit you should be having at least one L and one C. Both. Okay, means two energy storing device you should be having in the circuit. Resonance is a condition in an RLC circuit in which the capacitive and inductive reactances are equal in magnitude, thereby resulting in a purely resistive impedance. It is saying that for the resonance circuit, the capacitive reactance should be equal to the inductive reactance. Xc should be equal to XL. XL should be equal to Xc for resonance. Now resonance circuits, series or parallel, are useful for constructing filters, as their transfer functions can be highly frequency selective. They are used in many applications such as selective the desired station in radio and TV receivers. Okay. Come to the series resonance. In the series resonance, the elements will be connected in series. See here R, this is L part, this is the reactance given, and this is the capacitive reactance is given. They are connected in series combination. The current I is flowing and the input voltage is Vm theta. What is the impedance for this? If they are connected in series, we can add them. Z is nothing but input by current Vs by I, R plus j omega L plus 1 by j omega L, 1 by j omega C. This is the impedance. They are connected in series, so simply we can add them. So the impedance is R plus j omega L minus 1 by omega C. Now the condition of resonance is The resonance results when the imaginary part of the transfer function is 0. The imaginary part of the transfer function should be 0. Imaginary part is 0 indicates Xc is equal to XL. So they can eliminate to each other and become 0. The imaginary part become 0. So once you will equate this imaginary part 0, you will get over here omega L minus 1 by omega C equal to 0. When you solve it, omega L equal to 1 by omega C, omega square equal to 1 by LC, omega is nothing but root 1 divided by root LC. You know omega is nothing but 2 pi f. So instead of omega, I'll put here 2 pi f 1 by root LC. So f is nothing but 1 upon 2 pi root LC. This is your resonance frequency Fr in Hertz. So resonance frequency for series circuit is 1 upon 2 pi root LC in Hertz. Is it clear to you? So in the series resonance, the value of omega that satisfies the condition is called the resonance frequency omega naught. Thus the resonance condition means the frequency which satisfies this condition means the imaginary part will be 0 or the capacitive reactance will be equal to the inductive reactance. That frequency I'll tell the resonance frequency. This is the angular frequency omega naught L divided by 1 upon, and simply at the output you will get the resonance frequency in radian per second. It will be 1 divided by under root LC, and if you replace the omega by 2 pi f, you will get the resonance frequency in Hertz. Is it clear to you? Now what are the points in series resonance? In the series resonance, if series, they are connected in series, right? Inductor and capacitors part, they are connected in series. They are going to cancel to each other, so you will be remain with only resistance R. So in the circuit, the series resonance circuit will be purely resistive. The impedance is purely resistive, thus Z equal to R. In other words, the LC series combination acts like a short circuit and the entire voltage is across R. The LC combination becomes 0, means short circuit. Now the voltage Vs and the current I are in phase. Why they will be in phase? If input is Vs, current is I, why they will be in phase? Why? Because the I is flowing in the R. L and C, they both are cancelled to each other. So you are remained with only R in the circuit. So earlier we have seen in the phasor, in the R, the voltage and current both are in phase. Okay. The magnitude of the transfer function is minimum. The magnitude of the transfer function is minimum. Why? The transfer function is given output Is divided by input Vs. It will be like, see, we have seen the transfer function. It will be R plus JXC minus XL, whatever it is. Okay. Now what is going on? Or I can say in the other words, in the circuit, the impedance due to this 2 is vanishing, means it's going to 0. So you are having minimum resistance now or impedance in the circuit because these two are cancelled to each other, so you are remained with only resistance. So your impedance is reduced. If they are working in the circuit, they are providing their own behind the circuit. Now the fourth one, the inductor voltage and the capacitor voltage can be much more than the source voltage. The frequency response of this current magnitude is given over here. Please observe this. Frequency response. What is the frequency response? The frequency response of the circuit's current magnitude. See, current is given over here. The current will be the input voltage divided by R square plus omega L minus 1 by omega C square. Is it? Because this is the impedance, magnitude of impedance. Current will be Vm divided by magnitude of the impedance. Impedance we have seen earlier. Please don't confuse yourself. We have seen impedance over here. You need impedance magnitude. It will be R square plus omega L minus 1 by omega C whole square. And the root. This is the mod Z. So current is nothing but Vm by mod Z. Mod Z is given over here. The same thing we have used. This current. I can draw this current. The graph of this current will be like this. The current will be maximum. The current will be maximum when? At a resonant frequency. Why? Because at resonant frequency this part is going to be 0. Minimum resistance we are getting. Earlier we have seen this. Minimum resistance. Minimum resistance means current will be maximum. So this is the frequency in this graph given over here where the current is maximum and the maximum current is given by Vm by R. Because at the resonant frequency in the circuit you don't have the reactive parts. You are having only resistive part. So current will be Vm by R. But when you will look at it, to the circuit, you will find two more frequencies are given over here. This W1 and W2 is called the half power frequencies. Half power frequency, because the power at this stage is half. Okay. Or the magnitude is 0.707 of the Vm by R. Okay. Or the max value. Whatever the max value is there, the current max value is there. At the half power frequencies, the magnitude will be 0.707 of max. At the resonant frequency, the current will be Im. This is at resonance frequency. At half power frequencies, the magnitude will be 707 of Im. I hope this is clear to you. Now come to the bandwidth. The difference between omega 1 to omega 2 is nothing but the bandwidth. Okay, this is the useful thing for us. So we call it bandwidth. Omega 1, or I can say omega 2 minus omega 1 is nothing but bandwidth, denoted by B. Now come to the another term, and that is the quality factor. Quality factor of resonant circuit is the ratio of its resonant frequency to the bandwidth. So B is nothing but omega naught by Q. Q is nothing but omega naught by B. Is it okay? Or for the series circuit, if you equate these two terms, omega naught by Q is R by L. We need only Q. Q is L omega naught by R. Okay. So Q is omega naught L by R. This omega L for the series circuit is nothing but omega C. So instead of this, you can write omega C R. Both are equal. This is nothing but the quality factor. So friends, we'll meet again in the next class and we'll see the parallel resonance and we'll solve some problems. Okay. And then we'll start the graph theory. After this, we'll start the graph theory and then we'll finish the unit. Okay. So we'll meet again in the next class. Till then, take care and bye.